Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the very important concept of convergence, and let us briefly take a look at what we did the last time. And it is very important, the last lecture is very relevant for this lecture. So what we did was we defined the two notions of ultimately and frequently. So suppose we have some set X and a subset of it is given, then any sequence in X is set to satisfy this phrase, meaning we say that the point xn lies in a ultimately over n if there is some large enough natural number such that whenever little n is exceeding that natural number, the points in the sequence corresponding to this n lie in A. And this confirms with the English meaning of ultimately. So there's nothing to, this is nothing to memorize. This is already clear from the expression. Similarly, we have the notion of frequently. So we say that xn is in A frequently over n if, it appears, the sequence xn appears in A infinitely many times, and this is one way to express that. Alright, so these are the problems, and now let us move to the concept that we are interested in. So convergence will be defined only for real sequences. We won't be defining convergence for arbitrary sequences. It cannot be defined for arbitrary sequences just over a set, so let's forget about that. So what we have is, we have a sequence in R is said to converge to a point x or to x in R if for all epsilon greater than 0 there exists, or rather, okay, I don't say there exists. So for all epsilon greater than 0, the following happens. This is less than epsilon ultimately. So, okay, I've written something. I'll explain what this is trying to capture, but before I go there, this is not really looking like an expression that is, we should see something like this, because I'm using this phrase, and the way we define this ultimately thing was for things of the sort where A is a subset of R, and then I can ask, I can demand that xn is in A ultimately. But if you just decode what this is saying, one can alternately say that what this is saying is, for all epsilon greater than 0, xn lies in this interval ultimately. What is the spelling of this ultimately? But it should be clear already. I mean, we shouldn't need to all the time parse things in this way. Basically, any statement indexed by n, we can ask for whether or not it is true ultimately. So I won't be doing this kind of business every time. Also, let me write it in longhand. So this statement can also be written in this fashion. So for all epsilon greater than 0, there is some capital N, a natural number, such that whenever n greater than equal to n, we have so this is another way to express the same thing. All I did was I just expanded out the meaning of this, and this is the reason why this is a important definition, because every time writing this would be tedious. And in fact, this immediately captures what we are trying to capture, and let me try to say. what is that? What is it trying to capture? So we have this real line, and let's say we have some point little x, some real number, and we have a sequence xn. What does it mean for a sequence to satisfy this condition? So suppose xn is like, so let me color this in a different way. This is x, and xn, let's say, is orange. So we have this sequence, let's say this is x1, then maybe x2, and x3 could be here, and then maybe x4 is somewhere wandering around here. But saying that the sequence satisfies this condition is asking for the following. So suppose you fix some notion of nearness. So this is your, sort of room around x that you settle for. You can have arbitrarily stringent conditions, but let's say you choose some epsilon. Epsilon, it's up to you, it just needs to be positive. So suppose you choose it, and let's say it's 1/3. So then you have this, then you have an interval of size, the 1/3 on this side and 1/3 on that side. And what we are asking is that ultimately the points in the sequence come at least that close to x. Meaning, if you throw away some initial points in the sequence, then all the other points, they are all here. And this is true for no matter how stringent you choose your epsilon, no matter how small you choose an epsilon, ultimately all the points in the sequence will land up here. So what this is saying is that the points in the sequence get arbitrarily close to the point x. And once, not just that they come arbitrarily close, but this closeness has the property that ultimately this arbitrarily closeness is satisfied. So it's not like, we are not saying that this happens just frequently. We are asking that this happens ultimately. So just think about this. I think I've said it in many ways, but ultimately, I shouldn't use that word. But what I want to say is that the real understanding comes about only when you give it a thought as to what this is trying to do. Anyway, so another way to understand a definition is to look at specific examples as to what the definition is trying to capture. Before that, let me introduce some notations. So if a sequence xn converges to a point x, then x is called the limit of xn. That's just a definition. And notationally what we do is we write this. We write limit n tends to infinity xn equals x. So given a sequence and given a real number x, writing this is same as saying that this thing converges to x. There's just a shorthand for that. Or we may choose to use this notation, which xn arrow x as n arrow infinity. So we read this as xn tends to x as n tends to infinity, or xn approaches x as n approaches infinity, or xn goes to x as n goes to infinity, in whatever way you prefer. And we may also just write this where it is understood, where this part we just omit for brevity's sake. I would say that this is the proper way to write, which does not lose any information. There is no ambiguity here, but this is a shorthand. Okay, and let me also say that Let me just give one more definition and then we look at examples. So let xn be a sequence in R. We say that xn is a convergent sequence. If there is a real number such that so we say that a sequence is convergent if there is some point to which it converges. This is a natural definition of convergence. Okay, so let's see some examples and then move on. So our favorite example would be this. Let xn equals 1 by n. Then this sequence converges to 0. And this is really, we have done this in, we have seen this many times. Basically what is happening is, I'll just draw a picture. So we have this real line. Sorry. This is the origin, let's say, and suppose you choose some epsilon. This is epsilon. Then since the infimum of these guys is 0, beyond a certain point all of these xn's are here in this part. Beyond a certain capital N, whenever little n exceeds that capital N, xn will be here in this interval, and this is true for all epsilon. No matter what epsilon you pick, as long as epsilon is positive, this is true, and therefore this sequence converges to 0. So that's one example, and let's see one non-example, which is that let xn equals -1 to the n, then xn does not converge to anything. And what is the reason for it? So we have this, let's say this is the origin, doesn't matter. This is 1 and this is -1. And suppose somebody says that, well, suppose xn converges to some point x, and suppose the point is here. Suppose somebody conjectures that xn converges to this point. Well, this is of course not true, because you take epsilon small enough so that this is your interval x minus epsilon, x plus epsilon, meaning this much is epsilon. Then of course no point in this sequence is lying here, so we can forget about this sequence ultimately lying here. So the point is that if at all this guy converges to anything, that anything can either be -1 or 1. It cannot be different from these 2 points, because as long as x is different from 1 or -1, we can choose an interval around x which does not contain either 1 or -1. So there will be no point in this sequence which will lie in that interval. Okay, so what about 1? Can the sequence converge to 1? Well, okay, so choose epsilon again small enough so that it does not contain -1. This interval does not contain -1. And then it is not true that xn lies in this region ultimately, because xn falls out of this region frequently. It takes the value -1 at every odd integer, so it cannot ultimately lie here. So the conclusion is that xn does not converge to 1, and similarly xn does not converge to -1 for the same reason. So xn cannot converge, and this also leads to a definition that a sequence which does not converge is said to be a divergent sequence. A sequence which is not convergent is said to be divergent. So here in this example, we have this is an example of a divergent sequence. Okay, I'll perhaps introduce one more notation and then go to the next section. So here again we have a sequence. This is just a notation. So for a sequence xn in R, we write xn going to infinity, or rather, okay, let me start with that. Limit n going to infinity, xn equals infinity, or we simply write this, or we even drop the last thing to mean that for all real numbers x in R, or maybe I shouldn't use x. Okay, let me use something else. For all k in R, there is a natural number such that xn is greater than or equal to k if n is greater than or equal to n. So what this is saying is that suppose we have this real line. This is, let's say, the origin. Then suppose you choose some k. Let's say this is k. It could be any real number. Then ultimately all the points are here. That's what this is saying. This whatever this is written is same as saying that ultimately all the points are here, and this is true for each k. And that if you look at what this is, this notation is trying to say, it's a very apt notation. You will see that. And we say that xn goes to infinity. This is still a divergent sequence. A sequence which satisfies this is still a divergent sequence, because there is no real number to which it can converge. Such a sequence cannot converge to any real number, because it is going away from every real number in some sense in this direction. So, and if you want to see an example, the simplest example would be xn equals n. This is an example of such a sequence. So then this happens. And similarly, one can define this notation. So I leave that as an exercise for you to formally define this. And I might say that xn converges to infinity. I might read this as xn converges to infinity, but that is not to mean that xn is a convergent sequence. That would be just a slip of tongue. Now, as a remark, there is a more general framework in which you can think of it genuinely as a convergent sequence, but we won't look at that in this course. For that, we'll need to talk about general topology, which is something for the future. In this course, this will be treated as a divergent sequence. Okay, so now we get to the concept of null sequences. So a sequence xn in R is called a null sequence if it converges to 0. A very simple definition. So we already saw an example of a null sequence. Example was xn equals 1 by n. Then xn is a null sequence. We saw this earlier. Alright. And here is a very simple lemma. So let xn be a sequence in R. Then xn converges to x as n goes to infinity if and only if this sequence, this new sequence that we define, is a null sequence. So a very simple lemma. It just says that it reformulates the notion of convergence that we discussed above to just null sequences. And this is of course very, very easy, but let me give the full details because we have just seen this definition. So okay, so assume first that this is the case, that xn converges to x as n approaches infinity. Then we want to show that yn defined as this gives a null sequence. Meaning this sequence y1, y2, y3 dot 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 is a null sequence. Okay, so choose epsilon greater than 0. So let epsilon greater than 0. Then by definition of convergence, we have xn minus x absolute value is less than epsilon ultimately. Over n, which is as good as saying that yn absolute value is less than epsilon ultimately, which is another way of saying yn minus 0 is less than epsilon ultimately, which is another way to say that yn converges to 0. So that's the proof, and since all of these are if and only if, reversing these steps give you the other direction. So that's it. That's the proof. So it may seem a bit silly, but it's a good idea to do these things. Now a little bit more interesting lemma is that let xn be a null sequence and we have another sequence which we assume is a bounded sequence. Of course it is in R. So then this sequence is also null. Then this product sequence is also a null sequence. So again, this is also very simple, but let's do the proof. So what does it mean to say Bn is bounded? It says that since Bn is bounded, there is some real number, in fact a non-negative real number. In fact, you can assume or insist that it is a positive real number, such that there is a positive real number k such that mod of Bn, meaning absolute value of Bn, is at most k for all n. So that's exactly what it means to say that Bn is bounded. And now we want to show that xn Bn converges to 0. Okay, so let epsilon greater than 0 be arbitrary. Okay, and now by the fact that since xn is a null sequence, we have that this thing is less than equal to epsilon by k, I will write ultimately over n. And this is nothing contrived. Since this is true for each, I mean, whatever positive number I put here, this inequality is true ultimately. And the positive number that I've chosen is this ratio. And you'll see why. So once we have that, what we do is we get this thing times this thing is less than that ultimately. I need to add a page. And that implies this. So what happened here? Basically, this is equal to that. There is no difference. And here, this thing is at most, this thing is dominated by that thing. Because Bn is dominated by k and everything is positive, so there is no reversal of inequalities. So this gives us that xn Bn absolute value is at most epsilon ultimately. And that gives us desired. This is what we wanted to show. So very simple lemma again, but I want to say that the converse of this is false. So if you have a bounded sequence and another sequence with the property that this is a null sequence, that does not mean that this is a null sequence. Try to find an example. Very simple, but do it. Okay. So now we will prove some interesting properties of convergent sequences. So here is the first property. Every convergent sequence is bounded. So first let us see a picture and then we'll prove it. So suppose xn is a sequence which converges to, let's say, little x. So then what happens is, let's take epsilon equals 1. So this is x plus 1 and this is x minus 1. And since xn is supposed to converge to x, all points of this sequence are here except for the first few points. So maybe x1, x2, ... xn. These things are maybe not here, but everything else, everything beyond this capital N, meaning xn plus 1 and so on, are here. So those guys, the guys which are lying here, they are already, in a quote unquote bounded set. But what about the first few? So what we do is, maybe x1 is here, x2 is here, maybe x3 is somewhere here. Who cares? So what we do is we just take the maximum of all the first few things, along with whatever is the maximum of this and that bounds our whole sequence. So let me just do the formal details and it will be clear what I'm trying to say. So since xn converges to, okay, so I shouldn't start it this way. So let xn be a sequence, xn in R be a sequence, or be a convergent sequence, and say its limit is x. Okay, so by the fact that this converges to x, we have thus this inequality is satisfied, and I will choose epsilon equals 1. Which is, so what this says is that thus there is n, some natural number, such that whenever we have this, we also have this. Okay, which gives us the following. So here I have used triangle inequality. Again, from here to here it's a very trivial implication, but if you really want to give a formal argument in a neat way, what you do is you add mod x to both sides, and here you use the triangle inequality to get that. I mean, do it whichever way you like. Okay, so we have that the absolute value of xn is bounded by this number, and which implies, so from the above we get that this is less than maximum of this and these guys. Because when n equals 1, of course this is true, because the maximum of this will of course be greater than that guy, and on the left side we have mod x1, on the right side we have something, okay, let me put this symbol. So for n is equal to 1 this is true, n is equal to 2 this is true, because mod x2 is here, and for little n greater than equal to n this is also true, because 1 plus mod x is here and 1 plus mod x dominates this for all n greater than capital N. So that's it, and therefore whatever this maximum is a real number, which implies this is a bounded sequence. And that's it. Okay, and now for the last theorem. So let xn and yn be sequences in R, such that they are both convergent and the limit of xn is x and the limit of yn is y. So of course these are real numbers, x and y are real numbers. So we have picked two convergent sequences, x is the limit of the first one, y is the limit of the second one. So then three things: xn plus yn converges to x plus y. So limit n tends to infinity, xn plus yn equals x plus y. So the limit of the sum is sum of limits. second part is for any real number c, we have limit n tends to infinity cxn equals cx. So if you scale a convergent sequence by a constant, the limit is scaled by the same constant. And lastly, product. Limit n tends to infinity of the product sequence is the limit of the product, product of the limits. So we'll prove these three things. Okay, so here we go. So let epsilon greater than 0, and since xn converges to x and yn converges to y, of course as n goes to infinity, then we have two things. The first convergence gives us, I'll choose an epsilon by 2 here. Of course I can choose any positive number, which the first convergence gives me that this happens ultimately, and the second convergence, meaning yn converges to y, tells me that this happens ultimately. And since these two statements happen ultimately, they simultaneously happen ultimately. So that implies that both of these two things happen ultimately. Now if you want to, give a long-handed argument, there is some capital N such that whenever little n exceeds that capital N, this happens. And there is some n prime such that whenever little n exceeds that n prime, this happens. So then whenever little n exceeds the maximum of the two, maximum of n and n prime, both of these two things happen. And therefore that statement is condensed in this. That statement is what this is. That for all large enough little n, both of these two things happen simultaneously. So I'm saying something very simple. And since these two things happen simultaneously for all large enough n, their summation, sorry, I've written an x here, this is a y. This also happens ultimately, right? And now we use the triangle inequality. So what did we do? We just use the triangle inequality to say that this thing is at least as much as that thing. We just added these two things and put an absolute value around it. So that's the triangle inequality, and so this is equal to epsilon. So we get this, and since epsilon was arbitrary, this implies that the sum converges to x plus y as n goes to infinity. So that finishes the proof of the first part. Now for the second part actually follows from the third part. But I encourage you to write an independent proof. Don't prove it using the third part. And then, okay, so 2 exercises. First, give a direct proof of this thing. And then observe that it follows from here. Give an argument as to how do you use this one to get that one. And now we look at the proof of this. And so I'll just prove this. I'll leave this as an exercise. Second one is an exercise. And third one is what we'll prove. So I also encourage you to think of a proof of this for yourself before looking at the proof that I'm going to give, because that is instructive. but do look at this proof. This is a very neat way to prove this. So we want to show that, or rather, yeah, so let me write enough to show that this is a null sequence. That's what we observed, that when if we are able to show that this is a null sequence, we'll have shown that this thing converges to that thing. Okay, but observe that xn yn minus xy by high school algebra equals yn minus y times xn plus xn minus x y. Okay, and now this is a null sequence. Yn minus y is a null sequence because yn converges to y, and this is a bounded sequence. Why? Because xn is a convergent sequence. Every convergent sequence is bounded. We just proved it. Also, we showed that if you product a null sequence with a bounded sequence, you get a null sequence. So the conclusion is that this is a null sequence. Okay, so the first one is a null sequence. Great. What about the second one? For the second one, this is a null sequence. Yeah, I should use a different color. This is the null sequence. Why? Because xn converges to x. So this guy is a null sequence. And this is a constant sequence. Y. So this is in particular a bounded sequence. Every constant sequence is of course bounded. Every constant sequence is of course convergent. So it's bounded in, you can see it that way, but it's a very straightforward bounded sequence. So the conclusion is that this is also a null sequence. Okay. So what we have done is that the nth term in this sequence is expressed as the sum of nth terms of two null sequences. And as we already showed by part 1, if you have two sequences which converge to whatever limits, then the limit of the sums is sum of the limits. The limit of this guy is 0 because it's a null sequence. The limit of that guy is 0 because it's a null sequence. So this whole summation is a null sequence. This whole thing is a null sequence. And that's it. That's the argument. That's the proper formal argument that this is a null sequence. Hence, this thing converges to 0 as n converges to infinity, and we are done. So that's it. That's the proof. Alright, so some very basic properties, some very expected properties. There's nothing out of the ordinary happening, nothing counterintuitive, but proving this is very, very important formally, because otherwise what are we doing? Okay, so that's all. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.